Yes, good evening, friends. So let's start our next class on physics optional. So we are learning about Coulomb energies of mirror nuclei. Okay, we are learning about Coulomb energies of mirror. We are going to learn this. Now, while learning this, I had already told you that this particular portion for UPSC physics optional is to be learned very superficially. Okay, this particular portion. Other portions are not superficial. Other portions are to be studied properly, but this particular portion is superficial in nature. Okay, because the extent to which they ask the question is not very deep. Okay, so as they don't ask very deep questions and only one in one word everything is written in the syllabus, so this particular part doesn't require much understanding. It requires a bit of mugging up type of thing. Okay, so Coulomb energies of mirror nuclei. So what is mirror nuclei? We will learn that first. So two nucleides, okay, this is 2 t, two nucleides having the same number of nucleons, having the same number of nucleons. Okay, let me write properly. Nucleons, nucleons. Okay, same number of nucleons will be there. Now the number of nucleons is calculated with the help of a, capital A. Okay, same number of nucleons, that is, what does it mean? That is same A. Okay, same atomic mass number A, but different number of protons. Okay, but the number of protons is one, but the number of protons in one of them of protons in one of them is equal to the number of neutrons in the other. Okay, are called mirror nuclei. So there will be two nuclei. The atomic mass number, that is the number of nucleons, it is going to be the same for both of them. But the number of protons in one will be equal to the number of neutrons in other, and the number of protons in other will be equal to the number of neutrons in the first. Okay. So let me give you an example of mirror nucleus over here. So examples are very clear. H13 is there, suppose. Okay, and He23 is there, suppose. Then what is there in this? In this, Z is equal to 1. In this, Z is equal to 2. In this, atomic mass number A is equal to 3. In this also, atomic mass number A is equal to 3. Then what is the number of neutrons? Over here capital N is equal to what? And over here capital N is equal to what? So we can clearly find out capital N to be equal to A minus Z. What will it come out to be? 3 minus 1 is equal to 2. Okay. Similarly over here, N is equal to A minus Z. What will it be? 3 minus 2, and it will be equal to 1. So N is equal to your 1, N is equal to your 2. So clearly you can see this thing that Z and N are interchanged for both of these. Okay. The value which is there for Z here, it is for N here. The value which is Z equal to 2 here, over here N equal to 2. So number of protons and neutrons, okay, number of protons and neutrons are interchanged. Okay. Number of protons and neutrons are interchanged, and they are interchanged in such a way that A remains the same. Total number of nucleons or atomic mass number A remain same. Okay. So atomic mass number A remains same. In that way, these are the things which you know. Then there might be some other examples as well. Li 3 7, okay, and we have Be 4 7, okay. So what is the value of Z over here? Over here Z is equal to 3. What is the value of Z over here? Z is equal to 4. A is equal to 7. A is equal to 7. What will be the N neutron number? That is the number of neutrons. It will be A minus Z, which is equal to 7 minus 3, which is equal to 4. And over here N equal to A minus Z, which is equal to 7 minus 4, which is equal to 3. Okay. So 4 plus 3 is also 7, and 4 plus 3 is also 7, and 3 plus 4 is also 7. So this is basically your 4 plus 3 combination. Okay. 4 protons and 3 neutrons. And this is basically your 3 plus 4 combination. That is, number of protons is 3, number of neutrons is 4. Got it? So similarly some other examples are there. These are the other examples. Be, this is beryllium. This is your Be49, okay, and boron 59, and more examples. C613 means carbon 13, N7 13, okay. Then one more example is there for potassium and calcium 1939, and calcium 2039, okay. So write one note over here that the atomic mass number A for mirror nuclei will always be an odd number. So the atomic mass number A for a mirror nuclei, that is two mirror nuclei when they are taken, so the atomic mass number for them will always be an odd number. It can never be even. Okay. Only it will be only in the case of odd number of nucleons. Only case of odd number of nucleons this is possible, that number of protons and neutrons are interchanged. This is possible only in case of odd number of nucleons. You can check it yourself. Okay. So these are the things which you should take care of. Okay. Now Now we will move on towards the actual concept of this Coulomb energies of mirror nuclei. We will move on towards the actual concept. We learnt what are mirror nuclei. So we will learn about the Coulomb energies of mirror nuclei right now. Okay. Yes, so right over here then, if the odd nucleon, okay, let me write properly. If the odd nucleon, keep on making notes side by side, okay. If the odd nucleon changes from a proton to a neutron by positron emission, then total number of nucleons remains unchanged, okay, remain unchanged. Now let me write over here. Suppose I have nitrogen 713. Nitrogen has atomic number 7 and atomic mass number is, suppose I am taking the N13 isotope. Then what will happen? In this N13 isotope, it will change to C613 by the emission of a positron. Positron means E10. Okay, this is what is positron plus neutrino. You will learn about these reactions in the upcoming classes further in depth, but for the time being it is beta plus emission. Okay, so you will learn about it when you study the beta decay. So this has had 13 nucleons. So 12 plus 1 nucleons. Okay, 12 is even, so the odd nucleon changed to, suppose there are 7 and 6 over here, okay. 6 neutrons are there and 7 protons are there because atomic number is 7 and mass number is 13. So number of neutrons will be 6, right? So what happens is that the pair, if we try to form the pair of nucleons, then 6 out of here will form a pair, and one odd proton will remain. Okay, so if the odd nucleon means over here there was an odd proton. Okay, odd proton which did not form any pair. Okay, odd proton was there in this N713. Okay, so if it changes from a proton to a neutron by the emission of a positron, what is a positron? Positron is a particle which has all the properties of electrons. Okay, positron is a particle which has all the properties of electron except that electron has -1 charge and positron has +1 charge. Okay, so the opposite of electron, just opposite charge, all the other properties like spin, etc., mass, etc., all are same. Only thing is the charge is different for a positron. For electron it is -1, positron will be +1 charged. Okay, so when N713 emits a positron, this is basically your positron. Okay, positron. So when it emits a positron, it yields you C613. Okay, so it is yielding you a mirror nucleus, and in this C613 there will be 6 protons and 7 neutrons, right? Because 6 plus 7 is equal to your 13. So when odd nucleon, the odd proton which was left over here, 6 and 6 formed a pair, but one remained, okay? One odd proton changes from proton to neutron by positive emission, the total number of nucleons remains unchanged, because what happened is that the proton changed to neutron, right? The proton changed to neutron. So over here it was 7 plus 6. So 6 plus 1 plus 1 plus 6. Okay. So these 6 remain unchanged. This 1 changes. Okay. These 6 also remain unchanged. But this one odd proton will change to a neutron. And as soon as it changes to the neutron, a positron is emitted and the number exchanges. So this becomes 6 then, because one proton was changed to neutron and one neutron was created, so this becomes 7, right? So 6 and 7 situation arises out of 7 and 6 situation. Okay, so in this way, this is the meaning of this. And one neutrino is emitted. When you study the beta decay, you will understand all these things. It will come in the upcoming classes. If we assume, if we assume that the nuclear charge, if we assume that the nuclear charge is uniformly distributed, nuclear charge is uniformly distributed in a sphere of radius r. We are assuming the nucleus to be spherical and the nuclear charge is uniformly distributed inside that sphere of radius capital R. Okay. Then the Coulomb potential energy, then the Coulomb potential energy due to the Coulomb potential energy due to the nuclear charge is given as, this you will learn in the electrostatics. Okay, this you will learn in the electrostatics, but for the time being just remember this formula. Okay, 4 pi epsilon naught r, 3 by 5 q square. Okay, what is the formula? The formula is 3 by 5 q square upon 4 pi epsilon naught r. This is the actual formula. Now in the place of q, the charge of the nucleus is on account of its protons. So z number of protons are there in the nucleus, and the charge on each proton is E. So the overall charge on the nucleus will be Z into E, because Z is the total number of protons and E is the charge on each proton. So we will take its square and put it in the place of Q, which is the total charge. So this is the formula which is there. You learn about it in electrostatics, which I haven't taught yet. Okay, it is a part of paper 1. So this is basically your equation number 1. So the difference in electrostatic potential energy, now write over here. So the difference in electrostatic potential energy between the nuclei differing by 1 unit in Z is. Now why we are taking this, that difference in electrostatic potential energy between nuclei differing by 1 unit in Z? Because the mirror nuclei, because your mirror nuclei were differing by 1 unit in Z. Okay, because your mirror nuclei were differing by 1 unit in Z. So that's why we are taking the difference in electrostatic potential energy between the two. So that will be delta EC is equal to your, what will happen over here, you will put Z plus 1. Okay, over here you will put Z1 once and Z plus 1 once, right, or Z minus 1, because they are differing by 1. So when you take the difference of those two expressions, so what will be the difference? 3 by 5. What will be the difference? Let me write over here. The difference will be something of this kind: E square divided by 4 pi epsilon naught r, right? This is Z square. Okay, then minus 3 by 5, again the same thing, E square by 4 pi epsilon naught r. Then either it can be Z plus 1 or it can be Z minus 1, because depending on which you are taking Z. If you take the greater one as Z, then the other one will be Z minus 1. If you take the smaller one as Z, then the other one will be Z plus 1. Then we will take this common. Okay, what things are common over here? These things are common, right? These thing and these things are common, so we will take the common. So what will it be? 3 by 5 E square by 4 pi epsilon naught r Z square minus Z plus minus 1 square. Okay, then if you simplify this expression by using the formula a plus b whole square, what will happen? When you simplify that formula by using a plus b whole square, where will you use a plus b whole square? Over here. Over here you will use a plus b whole square. Okay, so when you try to simplify it, it will be something like this: 2z plus minus 1, depending on whether you took plus or minus, e square divided by 4 pi epsilon naught r. Okay, so this is your basically equation number 2, right? This is your equation number 2. Then what will happen? What will happen then? Now the things which I am going to write, those are basically you have to remember. Now write a note over here in the bracket. Okay, write in bracket, this is not a part of your notes, but I am notifying you something. Okay, whatever I am writing from here onwards, just note it down in your notebook. And mug it up. And mug it up. Okay, the reason for this already told in previous lecture I already told you this. Okay, simple questions are asked from here. Okay, questions based on this part is not for understanding. Okay. Based on this part, whatever questions are asked, those are very rectification type of questions, okay, mugging up type of questions, not based on understanding, okay. They ask very straightforward questions that explain Coulomb energies of mirror nuclei, explain mesonic X-rays, explain electron scattering. So all these are basically mugging up part. So you don't have to worry about that. So the now expression now which I am going to write, you have to just mug it up, okay. So what is the expression? Hence the maximum, note it down in your notebook. Hence the maximum positron energy when hence the maximum positron energy when daughter nucleus is formed in the ground state is given by, so it is given by this E beta plus is equal to 3 by 5 2z minus 1 e square divided by 4 pi epsilon naught r minus m naught c square minus mn minus mp c square. How are this coming? You don't have to go into it, okay. B nucleus, delta B nucleus. So how has this expression come? You don't have to go into it, okay. Just mug it up. M naught c square is the rest mass energy of the positron. M naught c square is equal to rest mass energy of the positron absorbed in creating it. Then Mn minus Mp c square is equal to your energy absorbed in transforming a proton of mass Mp into a neutron of mass Mn, and delta B nucleus is equal to difference between the nuclear binding energy in the pair of mirror nuclei. Okay, so now m naught c square is equal to 0.51 mega electron volt, mn minus mp c square is equal to 1.29 mega electron volt, and a is equal to 2z minus 1. So E beta plus is equal to, for whom we are writing all this? We are writing all this for this equation, this particular equation we are writing. Which equation? This particular equation, nuclear equation. Okay, for this nuclear equation we are writing this thing over here. Okay, so E beta plus is equal to 3 by 5. Okay, E beta plus is equal to 3 by 5 a e square divided by 4 pi epsilon naught r naught a to the power 1 by 3 minus 0.51 mega electron volt minus 1.29 mega electron volt minus delta B nucleus. Okay, so what will it be? 3 by 5 e square a to the power 2 by 3. Simply this a to the power 1 and 1 by 3, 1 minus 1 by 3 happened, and a to the power 2 by 3 was written, divided by 4 pi epsilon naught r naught minus 1.80 mega electron volt minus delta B nucleus. Okay, let this be equation number 3. Then what will happen? Now this is all mugging up part. Okay, this part you have to simply mug up. Then प्लॉट ऑफ, क्योंकि इससे इससे कुछ भी समझने वाले क्वेश्चन नहीं आते यूपीएससी में. मतलब यूपीएससी में ये वाला जो पार्ट है पर्टिकुलर, इससे जो क्वेश्चन आते हैं वो सीधे सीधे रट्टाफिकेशन वाले आते हैं, अंडरस्टैंडिंग वाले नहीं आते. तो इसलिए ये वाला पार्ट तुम सीधे सीधे रट लो. और तुम्हारे सिलेबस में भी इसको बिल्कुल सुपरफिशियली दिया हुआ है, ठीक है ना, इसलिए इसको रट लो सीधे सीधे. एमएससी कर रहे हो तो समझने की जरूरत है, नहीं तो कोई जरूरत नहीं है समझने की. स्लोप ऑफ द स्ट्रेट लाइन tan psi is equal to 3 by 5 e square divided by 4 pi epsilon naught r naught. From this, r naught is calculated, which is about 1.4 femtometer, which is about 20% higher than the correct value. Taking the Pauli's expression principle, taking the Pauli's exclusion principle under account. And if you want to watch the previous lectures, then you have to go into the link in the description. Okay, under that account, it is found that R naught is equal to 1.23 plus minus 0.03 femtometer. And how does the graph look like? The graph looks something like this. Okay, the graph will look something like this. This is a straight line, by the way. Okay, so the graph goes like this. This is your psi e beta plus a to the power 2 by 3. Okay, this is how the graph looks like. Okay, so this is a mugging up part, so I just wrote everything just like that. And the mugging up part is coming once again. In the next lecture we will look at neutron scattering method. Okay, so that is also mugging up part only. Okay, so thank you very much. I am coming back in some time. So we will look at the neutron scattering method now. Again, it is also mugging up method. Okay, a method to mug up. So neutron scattering method. Neutron scattering method. A fast neutron, a fast energy 10 to 50 million electron volt passes easily through a bulk matter. Of bulk matter as it is chargeless. If reduced de Broglie wavelength lambda cut be the reduced de Broglie wavelength of the neutron, then scattering cross section for direct encounter of the neutron with the target is found to be sigma absorption is equal to pi r plus lambda cut square. Okay, this is your equation number 1, where r is equal to your nuclear radius. Nuclear radius. If we take the wave aspect of the neutron into account and treat the beam of neutron as a plane wave, then for the fast neutrons lambda cut smaller than r, and for small angle scattering, the scattering cross section is again found to be sigma SC is equal to pi r plus this whole square. This is your equation number 2. Okay. Now how this has come, you know this very well, that pi r square will be the cross section of the nucleus. So lambda cut will be added to it because neutron scattering is happening. Okay. So thus the total scattering cross section sigma t is equal to sigma absorption plus sigma SC, that is sigma t, or sigma t is equal to 2 pi r plus lambda cut square is equal to 3. Equation number 3. So now write down, it is about it is about twice of the effective geometrical area of the nucleus using the experimentally measured value of of sigma t, the nuclear unit radius is found as r naught is equal to 1.4 plus minus 0.1 femtometer. So in this way you are, this is all these things which I have written over here, you have to note it down in your notebook and just mug it up. There is no other way, no other option. Then the alpha scattering method we will do in the next class, and in this alpha scattering method which we are going to do in the next class, there will be some understanding required. Okay, so the next part that comes over here will be of understanding instead of mugging up. Okay, so thank you very much.